preparing live stream. Live stream is also going. Okay. Huh? Did I unmute anything? Or?
No. I think they shared the wrong screen.
Oh, okay.
It's better now, right? Zoom is fine. So I guess YouTube also. Before, it had this thing for.
Part of the study.
Okay. I think
Fine.
now YouTube will catch up.
Yeah.
Okay. Okay, so let's get started. Maybe we can close the door also. Okay, so let's get started for another session of seminar in computer architecture. I hope you guys are enjoying from the past lectures. So Rakesh and I, we are going to deliver today's lecture on machine learning driven memory and storage system design. So hopefully through the today's lecture, you would be much more evident what exactly do we mean by this thing. So this is our brief introduction. Rakesh and I both are PhD students, well, past and current in Safari Research Group. We have previously worked on various capacities in different companies before joining our PhDs. And these are the email address that you can reach us to if you have any questions regarding today's lecture, or in general, if you have any other ideas that are spawning out from today's lecture. Okay. So in general, like broadly, we are interested in microarchitecture, memory and storage subsystem design that includes let's say high performance, memory storage system design like prefetching, cache management policy, storage system device, management policies, and so on. So we are also focused in our research on data-driven architecture. So data-driven, hopefully this is going to be much more clear as I go through, like how exactly we can make the architectures much more, take more informed decisions by learning from the data that it's observing. Okay. So just so let's get started. So you have seen probably some version of this slide again and again, like, computing is, as it stands today, is heavily bottlenecked by data from large scale recommendation systems, genome sequence mapping. There are other, like, not only just the workloads that are running on servers, but also workloads that we are using in our mobile phones. For example, Chrome browsing, all the way to video capturing and video playback, everything is heavily bottlenecked by data. So data contributes to the major performance and energy bottleneck of these systems. And also emerging workloads like genome sequence processing, right? So all of these workloads are generating tremendous amount of data that we can't even process at the current pace. So the axiom of designing a better architecture that would be good fitted for the future is that intelligent architecture should handle the data well. And what do we mean by the data well? So as it stands today, today's architecture are very terrible at dealing with the amount of data. So broad part of the data is broad part of the processing is the processor is mainly dedicated to store the data rather than compute on the data. So you have seen version of this slide in the previous lectures of memory-centric computing, right? So that's what we have also demonstrated in the past lectures, that processor-centric as opposed to be data-centric. So today's computation is very much processor-centric, and then we have shown examples of becoming data-centric processing. We would also see, and at the part of today's lecture, we are going to show this thing, that the architectures that we have designed, they're in general very much terrible at taking the advantage of this data that they can see. Like to give an example, let's say our phones are seeing so many applications that we are using in the day-to-day life, right? Still, the memory controllers that our phone has been designed with, the processor in the phone has been designed with, they're probably taking the same decision again and again throughout the entire course of the device, even though you are probably using that device different in the way that someone else is using the device. So in some sense, they are not fully learning from what data that they are observing at runtime. And so that's what we call it, that they take human design driven decision, like what we as a human designers have designed it to do at runtime, as compared to taking data driven decision. And this is what we are going to see, how we can make the architecture to make more data driven decisions. And the other part of the lecture, which we are probably not going to discuss at today's point, but maybe in somewhere in the future, that they're also terrible at knowing and exploiting different properties of application data, in a sense that they're designed to treat all pieces of data in the equal importance, even though they are not. So we call this thing that they take component aware decision as opposed to taking data aware decisions. So to break through these limitations, the axiom that we have is to make the architecture data centric, data driven, and data aware. And I think you have also seen this slide before, and this slide has diverged to data centric architecture design in the previous lecture. So now for the course of today's lecture, we are going to look into data driven architecture. Okay, so as I said, like what the today's architecture is, that it's human design driven. We design the policy, how to do things, and as a result, when we as a human designer would design some policy, it often comes out to be very short-sighted. So we can't anticipate the consequences of the action that we are taking now, how exactly it's going to impact in the future. So what we and then there is very less adaptability to enable data driven policy learning. And then as we discussed, like almost no learning, so they often do not learn from the past actions. So the question is that, can we design fundamentally intelligent architectures that actually take or make use of all the data that it's seeing? Data meaning like not only the application data that you are using, but also the system generated data. Let's say, oh, if I do this action, then my bandwidth is getting consumed. So should I take some other action that relaxes the bandwidth or not? So anything that is, any data that is not only coming from the application, but also the system generated data. Okay, so that's what we are going to look into the data driven architecture, meaning that it learns the best policy as opposed to we as a human designer telling it what the best policy is. And hopefully I'm going to convince, and Rakesh and I both are going to convince that these sort of policies are possible to design inside the processor with decent or let's say minimal hardware complexities. Okay, so let's get started. So this is the overview of the memory hierarchy that we have probably seen, I think, or already that this is inside you have core, and you have the local private caches, then you have the last level cache, you have the main memory, which is backed up by the storage system. So for the course of today's lecture, we are going to look into some proposals that we have proposed in the past. So we are going to start with a reinforcement learning based prefetching solution, which is going to prefetch data from the main memory to the on-chip caches. So that's one example that I'm going to show. The second example that we are going to show is a perceptron based off-chip load prediction, which actually sits inside the code and predicts which request is supposed to miss the entire cache hierarchy and would come to DRAM and then would start accessing the DRAM. And how can we embed machine intelligence inside making that prediction? So we are going to look into that. And then the third proposal that we are going to look into is yet another reinforcement learning based coordination policy that manages these two mechanisms together. So these three in general going to be the first part of the lecture, which I'm going to cover, which is depending on the memory system. And then Rakesh is going to cover the second part of the lecture, which is on the focusing on the storage subsystem. So if you have, let's say, hybrid storage system, which is comprised of a fast storage as well as a slow storage, which we are showing over here as a, this is like an Intel Optane SSD as well as the normal, the hard disk drive. And then in this sort of say a hybrid storage system, how reinforcement learning can be used to make data placement decisions as well as data migration decisions. So that Rakesh is going to cover. Okay, so let's get started with the reinforcement learning based hardware prefetching mechanism. So how many of you know what a prefetcher is? Anyone? Anyone have taken any DDCA lectures? Okay, so I'm seeing some hands. So maybe I can give some like a very brief introduction. So what prefetching is, prefetching, as the name suggests, that you're going to fetch the data before it is needed by the program. So that's the name, prefetch, right? So why? Because we know that memory latency is really high. So if we can prefetch accurately and early enough, then hopefully that prefetch request is going to cover for your demand. When the processor actually demands for the data, it would already find the data inside your faster memory. So it can eliminate compulsory cache misses. That's all. But then how exactly we can achieve this speculation? Like how on earth we can imagine that, okay, processor is going to need this address in the future. So that's basically involving the prediction of which address would be needed in the future. And it really works well if your program has predictable address pattern. Let's say, oh, you're iterating through an array, right? So that generates very regular memory access stream. In such cases, maybe it would work really well because it can anticipate well before the program actually demands it. But in many other cases, it can also fail gloriously if you don't predict it correctly. So here are some examples of, let's say, some predictable address patterns. So you can see, like in the first example, it's just simply, so all of these are cache block addresses. So you can see there is a stride of 1. So it's basically streaming through the entire memory space. So here it's a bit complicated. It's not exactly streaming, but it still has some sort of predictable strides, right? So it has a stride of 42. This is even more convoluted than the previous one. So here you can see that, oh, the first stride is 2, the second stride is 3, the third stride is 4, and then again 2, 3, 4, and then again 2, 3, 4. So there is some sort of increasing order of complexity what you can predict. So you can design, and literature has proposed lots of prefetching mechanisms that can progressively identify more complex patterns. So here is another pattern. It's seemingly looking like completely random, but if you still look in closely, you can see that, okay, X, Y, T always repeat. So if you see X, you know that the next would be Y. If you see Y, then you know that the next would be T. Maybe there are some other patterns also, but let's not go there. Okay. And then you have patterns like this, which is probably seemingly random. But if you still look inside, like, oh, A plus 1, 67, A plus 8, and A plus 7, 99. So this follows in one cluster, and then the same cluster repeats, and then the same cluster repeats. So just to give you an example, like how complex the memory address stream can be, the better your algorithm is, the better you can understand what your program is supposed to access next. Okay. The question is that does prefetching affect correctness? The answer is no. That you're still doing a best effort to bring the data to the closure memory, but even if it's wrong, then it's not going to affect the correctness of your program execution. But that does not mean that it's not going to affect anything in the system. So it has useless data prefetching also has secondary effects. Like, for example, it would consume memory bandwidth. It can also do cache pollution, meaning like you fetch the data inside the cache, and then you don't need it. So then the cache would be simply you're actually evicting something out of the cache which could have been needed. It also wastes energy consumption and so on and so forth. So to evaluate prefetcher, we look into many metrics. One of the metrics for that reason is that the accuracy. So accuracy meaning that how many of the used prefetch how many of the sent prefetches are actually used. So if you have an accurate prefetching, then the more accurate, the better we want. So these are the metrics that we have. We typically use accuracy, which I just said, coverage and timeliness. Coverage meaning that, okay, how many of the requests that you can cover. Timeliness meaning that how far ahead in the program you can actually anticipate. So that's what the timeliness is. Then there are other metrics also which are equally important with these three. For example, bandwidth consumption, like how much bandwidth that you're using for making this prefetching, and then also how much cache pollution that you're contributing. Now, more often than not, when we design a prefetching solution, we often overlook these two metrics. We typically chase for these three, and as you can imagine, like these three are also very let's say not easy to co-optimize, because if you have, let's say, high accuracy, then your coverage goes down. If you have high accuracy, high coverage, then maybe your timeliness can go down, and so on and so forth. So these three by itself is very hard to optimize. And then when you start considering these two matrix, then it becomes even broader challenge. So this is one example of that broader challenge. So what I'm showing over here, on the x-axis, you have different workloads. Y-axis, you have instructions per cycle. So higher the bar, the better it is. Okay. Now, these are the 4 prefetching mechanisms that we are considering. No prefetching is the baseline. You don't have any prefetching. So that's what your program behaves without any speculation, right? And then you have some conservative amount of prefetching. Then you have a very aggressive amount of prefetching, and then you have something in the middle of the road. So the anticipation is, if you look into the geometric mean of all these workloads, so what you see, so if you enable prefetching, whether it is conservative, middle, or very aggressive, you actually see performance improvement. So which is good, that prefetching is working. But then if you look into some other workloads, like these are the 2 specific workloads, what it's showing that the more aggressive you become, the performance actually tanks. Why? Because in those cases, probably not only so not only these 2 matrices is what is concerning, but also these 2 matrices are probably coming to the picture. So what might be happening is that you are consuming so much of bandwidth, then your demand is also falling behind. So the more aggressive that you go for prefetching, the performance tanks. But you can easily see that this is not also globally true. So how would you know that when your aggressive prefetching tanks, when your aggressive prefetching helps? So that gives us this dynamic behavior that, okay, we need to have some sort of a dynamic understanding from the system that how my prefetcher is interacting with the system, and dynamically optimize as required. So that gives this idea that, okay, let's have some sort of a feedback directed prefetching, right? So ideally the idea is that, okay, we monitor some sort of prefetcher matrix on the fly and try to see what decisions we need to make. So you can easily create some sort of a like a decision tree like this, that if your prefetcher's accuracy is really high, if it is not late, and if it is but polluting, then you make the aggressiveness of the prefetcher to be lower. Why? Because it's polluting the cache. But if it is high accuracy, but it's late, let's increase the aggressiveness so that we can predict it much ahead of the time. Similarly, you can also easily argue in a human way that, okay, how this let's say decision tree would look like, and you can come up with like a feedback mechanism like this. But the problem of this feedback mechanism is like, okay, what you consider to be high accuracy? You would obviously, as a human, we would obviously come up with some threshold that, if the threshold is more than 70%, that I'm not calling it high accuracy. But what gives you that understanding that, okay, this threshold is the correct threshold to check? Because what is high accuracy for, let's say, workload 1 might not be high accuracy for workload 2. It might be even more sensitive for even small number of inaccurate prefetches, right? So that actually gives this sort of big playing field. So here what we are showing over here, that okay, if you look into this FDP, what we just showed beforehand, so FDP actually improves performance not only in geomean, but also these 2 workloads which we showed before, right? That aggressive prefetching actually hurts. So that's this very aggressive bar. In those cases also FDP works. But then the question that I raised, like, okay, FDP works because you created that decision tree, but the decision tree is obviously backed up by some thresholds. Why that static thresholds? Why not make it dynamic? Because static threshold also has that inherent behavior that, okay, it might work for one workload, it might not work for different workload. Or maybe if you change the design of the processor, then you need to probably retune again. So that's the whole idea of the the paper that we are going to present, that okay, let's methodically try to formulate prefetching as a reinforcement learning problem. So we just go back to the drawing board, and then let's try to formulate how can we learn from the system on the fly without relying on direct parameters like those static thresholds and so on. Okay, so before going there, this is just a brief background of the basics of reinforcement learning. So it's an algorithmic approach to learn to take actions in a given situation to maximize the numerical reward. So so any RL system is comprised of an agent which sits in an environment, So for every time step, agent senses the state of the environment, takes an action, and for every action, the environment also provides a reward. And the goal is that, okay, the agent stores something called a Q value for every state action pair. So that Q value essentially represents what's the expected return of taking that action in that given state. The idea is that whenever you are at a state, you would take that action that gives you the highest Q value. So basically, it's a greedy approach. You go on. Okay, so it seems like that the hardware prefetching actually fits very nicely with reinforcement learning framework. So in this case, the prefetcher itself acts as the RL agent, processor acts as the environment. You can sense multiple state information of the demand request that is trying to generate the prefetch. For example, let's say, which program count or which load instruction is generating this memory request, what you have seen in the past, what sort of strides you have seen in the past. Every type of information, you can think of this as a feature that would tell you to what to prefetch. So in this case, the offset is like the prefetch is basically detecting that offset that you are going to add to your current address to get the prefetch request. And then for every request, you are also going to receive a reward that you would use to train this prefetcher. So let me just give you a brief example of what exactly does this mean. So as I said, like the state is essentially a k-dimensional vector of features, and feature is comprised of both control flow and the data flow information. Control flow information is as anything that encodes how exactly the program is executing, like on a PC and the branch PCs, last 3 PCs, anything that you can think of here. Similarly, data flow example can also be, let's say, cache line address, physical address. All of these information can be like a state information. What is action? As I said, like action is just selecting this prefetch offset O. So you can calculate by yourself that if you are restricting yourself within a prefetching within a page boundary, then you would end up within 127 actions. And just to put it into perspective, 0 offset is actually a valid action in this case. If your agent decides to pick 0, then it means that it's actively deciding not to prefetch anything. Okay, and then we can also do some fine tuning of the actions by offline pruning to make the search space smaller. Now, the third part, which is the most critical part of PTI, is basically the reward. And reward is essentially what defines the objective of this prefetcher, like what exactly it should do. Now, in this case, we are encapsulating two matrices, like prefetch usefulness as well as the system level feedback. So what do you mean by feedback? So these are the reward levels that we have defined. Like, so this is accurate and timely, accurate but late, loss of coverage, inaccurate, and no prefetch. So these two rewards, they have their further subcategory of the rewards based on what bandwidth consumption is. So the rationale here is the following. So if you know that your bandwidth consumption is high, then it might be good to do nothing as compared to do something inaccurate. But on the other hand, if your bandwidth consumption is low, then you might actually trade off some inaccurate prefetch as compared to doing nothing. So that's the whole idea. So all of these values are essentially some static values that we have set at design time, but you can also customize it in Silicon, change it, provide a different number to customize the prefetcher in the get-go. Okay, so I'm going to probably skip through these 2 slides because that's probably going to too much into detail. But so these are the configurations that we finally ended up with in prefetch like Pythia. So Pythia is consumed of 2 features, 16 prefetch actions. So that has been pruned down. So out of these 16 actions, you have negative delta, 2 also positive delta, and 0 is also a valid action. And these are the reward hyperparameters that we ended up with. But these values does not mean that these hyperparameters need to be fixed like this. So there can be future work that can also say, how can we even change these parameters on the fly? So we have shown that, okay, if you change this parameter using hardware counters, your prefetcher, the same hardware design would work differently. But one good future work can be that how can we even tune these parameters on the fly? That's also another possibility. Okay, so I'm not going to go through this much of detail, so that's probably too much. So let's go to some evaluation numbers. So this is what we evaluated Pythia with. So on the x-axis you have number of cores, y-axis you have the geometric speed up. So higher number is better, and so this is what the previous prefetches looks like. So these are these three lines, and this is what Pythia is. So as you can see that Pythia is not only good in one core, but it is also moving the front across the board, right? So across all the core configurations that we have evaluated, it increases the performance. So that gives an understanding that okay, it's not only good for one configuration, system configuration, but it can adapt by itself. So on single core we have 3.4% performance benefit. If you go for 12 core system, that has 7.7% performance benefit. So some reason this fonts are off, but you can understand what I'm saying. So we also did some study on varying the DRAM bandwidth. So on the x-axis, you have different bandwidth. So the more you go on the positive x-axis, you have higher bandwidth. The more you go on the negative side, you have lower. On the y-axis, you have the geometric speed up, so higher is better again. And so this is what the previous prefetches used to look like, and then this is the red one is what Pythia is. And all of these bandwidth points are actually coming from real processors like this. These processors, like the names that we have mentioned over here. So these processors, the single core of the processor is operating in this bandwidth point. So what you are seeing over here is that Pythia not only improves performance when you have the ample bandwidth, but it also increases performance benefit when your bandwidth is really congested. So that gives another feedback that this is not only good in one configuration, but it's also dynamically adapting based on the system configuration that you are seeing. Okay, so if you're interested, all of these things are open source. This has been extensively used inside industry also. Believe me when I'm saying this. Has been used in industry, but if you want to extend, the idea, there has been multiple possibilities to even improve Pythia further. So feel free to check out the repository if you, and these are some prior lectures that we have delivered. So if you're interested, definitely go through them. Okay, so that concludes Pythia. Do we have any question till now? Okay, one. Tell me.
The parameters that you configured for a RL system like the RAH.
Correct. Yes. Yeah. Those rewards. Yes.
Like, how did you calculate that? And you were saying that they are on the fly. So, like, how can we make them on the fly?
Okay, that's a good question. So, how do we set them? So, in the paper we have mentioned like there is automated design space exploration framework. So you can test. So this is like machine learning model tuning, right? So you have some workloads that you take it out as a test workload, and you are going to work on those workloads, try to see which parameters are working the best, hyperparameters, and then you test with all the other workloads, saying that okay, this is generalizing now. So that's how, and in the paper we have like all the scripts. In the repository, you would also see the scripts, how we did these things in an automated design space exploration. That's it. How can you improve it upon? So you can think of these hyperparameters as, let's say, something that is also dynamically adaptable. Right? Like if you let's say make some random perturbation in the parameter, see how the prefetcher is behaving, and then try to go in that direction. So this is like stochastic gradient descent, right? Like, so you make some random perturbation, see whether that gradient is working. If that's the case, then you go on that gradient and then keep increasing to go there. The moment you see that okay, that is probably hurting, then you come back. So you can also think of tuning those hyperparameters on the fly. That can be actually a good future direction. That's a good question. Any other question? Okay, so if not, then let's go to the second one. So you saw one prefetching mechanism that basically tries to anticipate what addresses are going to come next. Correct? Now, can we do better? So what we saw, and I'm not going to read this thing, and I'm going to show you this. So long latency loads that actually go to main memory, they are the key limiters of performance. We all know this thing. But and for that exact reason, we have also sophisticated prefetchers like one I just showed, Pythia, Another one is another option is just, oh, you keep on increasing the size of the caches. Right? That also works, because the bigger the size of the cache, the less number of memory requests would go eventually to DRAM. Right? Guess what? So even if you have state-of-the-art preparation, and in this case we are evaluating Pythia in this case. So out of the entirety of the pie chart here, so that pie chart represents all the load requests that would go to DRAM if you don't have prefetcher. If you enable prefetcher, half of them are gone. So that's your prefetcher's coverage. Half of them are perfectly predicted. They have been brought to cache. But the remaining half still goes. Remaining half is still going to the DRAM, and they are the one that is causing performance problem. Now, 70% of these half are also the ones that are stopping the out of order processor to even progress. So there is something called the reorder buffer. So that kind of executes the instructions out of order. That is getting stopped. So the commit from this reorder buffer also gets stopped by 70% of these 50%. So they are the most performance critical loads. So what to do for those loads? What we saw is that on-chip cache access latency is not a small latency anymore. And if you reduce this on-chip cache access latency, take it out from the critical path. So what do we mean by critical path? So what would happen in the baseline system? You would look up L1, L2, LLC. You would not find anything in the cache, and then you would access the main memory. But if you know that if it is going to main memory, you can literally start accessing the main memory while you are accessing the cache hierarchy. So that's basically what we are calling taking this on-chip cache access latency out of the critical path, meaning that this latency is now hidden by this latency, because main memory access is anyway longer than what cache access would be, right? If you do that, this number of cycles you can save, and that's actually huge. So we showed in this paper that 40% of the stalls caused by these loads that are going to off-chip can be reduced if you simply take out the on-chip cache access latency from the critical path. So if you can make it parallel, that actually works. But then the question is when you want to make this decision, because you can easily imagine like, oh, you need to predict who would eventually go to DRAM, right? Otherwise, if you start accessing DRAM for all of them, you're screwed. You can't progress, right? So then your DRAM would be getting access much more than what it would have been done in the baseline. So that's what we try to motivate on this regard. Like this latency is also increasing at a rapid rate. So we have seen this is 2007 paper. They also showed that on-chip cache sizes are increasing, and so is the latency. We also did some study which also showed the same trend, like L2 size is increasing, and so is the latency. It's just a fun fact, and I say this whenever I present these slides. So when I was working on this project, this was the main processor configuration that I had at that point. So this is 2021. This paper was published in 2022. So at that time, by the time I actually presented this paper, Intel came up with another processor that increased the size even more and increases the latency one cycle more. And now, right now, we have another 2024 version of their microarchitecture that again went to the same step. So it has gone even more higher size in L2 and even one cycle more. So now the L2 latency sits at 17 cycles. So you can easily see that, okay, the trend in the industry is that you would have bigger caches. Why? Because your data footprint is also growing. But with bigger cache comes bigger latency. So we need to do something for those aspects. So that's the goal of this work, that, okay, we can improve performance by removing the on-chip cache access latency from the critical path of these objects. So that's what Hermes is. So Hermes, what does Hermes do? It is essentially going to predict in the very beginning of the memory instruction, which memory instructions are likely to go off chip. And for those predicted requests, it would start fetching the data directly from the main memory while also concurrently accessing the cache hierarchy. So that's the whole idea. Now, so how Hermes works? So this is exactly how it works. So this is the baseline case. As I said, like what you would do, you would access the L1 data cache, L2 LLC, then memory controller, and off-chip memory. So this is what your timeline would look like. And your processor is also designed with the reorder buffer, which basically sustains the memory access latency. And at some point, your reorder buffer would be full, and everything else for the rest of the part of this memory access, your processor would stall it. Nothing can be done, right? Now, if you have, so what Hermes proposes, it proposes a perceptron-based off-chip load prediction. So this perceptron is what the memory or the data-driven aspect of this project is. So I'm going to come in the next slide. But what this Puppet is doing, so it's a perceptron-based off-chip load predictor, which sits inside the core. What it does, it basically, whenever core generates a memory request, it consults this predictor, says, oh, tell me, is it possible that this load would go off-chip? Puppet, if Puppet says that, yes, you know what, it might go off-chip. What would it do? It would start accessing the L1 data cache, and it would also access the translation. Like, keep this in mind. I'm not sure whether you have already exposed to this concept. So whenever program executes, it generates a virtual address. But your main memory and everything is addressed with a physical address. So you need some sort of an address translation that translates a virtual address to the physical address, which happens beside the L1D lookup. So you would still wait for the L1 data cache lookup for the translation to finish. And the moment you know which physical address it should go, your predictor already said that it would go to main memory. So you would start accessing the main memory. So that's the whole idea. So you cross-cut the entire thing. But that doesn't mean that you are not looking up the cache. So you would still look up the cache. If your prediction is indeed correct, this request would eventually arrive at the memory controller. At that point, memory controller would say that, dude, some request is already went outside. Just wait for that request to come back. Eventually, that request would come back from the main memory, because still your main memory access is slower than your entire cache access latency, right? So you would wait here, and once the data comes back, then memory controller would say, okay, give back the data. So what you actually achieved, you literally achieved this overlap. So your L1 latency is not hidden. Why? Because the translation happened beside this. But then L2 and LLC latency is actually hidden behind the main memory access latency. Why? Because main memory started you started accessing main memory in parallel. So what you did to do, so you essentially save these many stall cycles that could have otherwise stalled the processing. So that's the whole idea. Okay. Yes.
So in this case, you was that L1 cache is virtually cached, and from L2 is physically.
That's correct.
And what if the design of the architecture is different?
Why is that?
No. I mean, so probably you can also do it differently. So like, let's just do the virtual address, virtual caching from, like, let's say lower level cache. So until L2, just make it virtual cache, and only from LLC physically cache, then this should also be changed. Or
so, okay. So if I'm not mistaken, so your question is, if my L2 is virtually addressed, then does this need to change?
Yeah. Exactly.
No. So what your short circuit path is trying to access is the main memory.
Yeah.
Your main memory is still accessed by the physical address, right? So you can still cross-cut this entire hierarchy, even if your L2 is made virtually addressed. Does it make sense?
Yes, then the translation of the virtual address still just happens at the same time.
Yes. So your virtual address to physical address translation typically. So there are translation cache also, like we call it TLB, translation look aside buffers, right? So TLB access actually happens very similar time of the L1 data cache. So it is like very similar in time, like 4. So if this takes 5 cycles to access, TLB would probably take 4 cycles to access, or maybe 5 cycles. So that's why we say that, okay, L1 access latency and the TLB access latency is kind of same. So the fact that I'm showing that this latency is here, it's not that L1 data cache access latency. It's actually the TLB latency that I'm not covering. So that part you still need to switch. You can't cover, like you literally can't push it here. You have to pay some latency for the translation to finish. And the moment your translation is here, then you start doing this thing. Does it make sense?
Yeah.
Okay. Any other question? Okay. So yeah. So and then when the data returns back, then you are supposed to, we are going to train this predictor. So let me show you how exactly this predictor works. So this is a multi-feature hash perceptron model. So we meaning the architects have actually used this type of model for making the branch prediction. Branch prediction meaning that, given a conditional branch, like you write if else code, right? So given a conditional branch, this sort of model had been deployed, and it has been deployed in the actual processor. Like if you're using Samsung phones, Samsung Exynos processor actually has this model for predicting branch outcomes. So if you have if you're writing code like if else, whenever your program executes there, it actually makes a prediction whether should I execute if or else. So that's what these sort of models are trained for. This is a Boolean value. Should I take the branch or not take the branch? So that's what it does. So what we are doing here is we are actually repurposing that sort of model for our prediction case. So in this case, we want to make a prediction, okay, whether it would go off chip or not. So that's what happening in this case. So what we do, we essentially extract multiple features from a given load instruction. So this is what I'm going to show you, like how exactly the prediction works. So when you see a code generates a memory request, you extract a bunch of features. Features in this case, let's say, oh, what is the memory instruction that is generating, and what the cache line offsets that is going to. Now, this is one example, right? You can literally have multiple other features, and in the paper we have, I think, 16 features we have tuned with, and then all of these features would be hashed down, and the hashed value would be used to look up this weight table. And once this lookup is done, the weight table is going to give you some weights for that specific feature. So in this case, let's say this is -4, 12, and -5. So what does exactly weight means here? So weight can actually range from, let's say, -16 to +15. So it's like a 5-bit signed integer. Okay. So sorry. So if your weight is closer to 0, it means that you have seen equal number of samples that, as with that feature, equal number of samples went off chip and equal number of samples went on chip. So that's why the weight basically is not either on the positive side or the negative side. It basically sits right in the 0. So if it is 0, it means that it's neither positively correlated or negatively correlated. If it is either on this side or that side, it basically provides a correlation. So this is like a Pearson correlation sort of, you can imagine. So if it is positively correlated, it means that, oh, whenever that feature comes in, you know that this would go off chip. If it is negative, for example, this is what the value is. When it is negatively correlated, let's say if it is -16, means that whenever that feature value comes up, it's definitely not going to go off chip. Something like that. Okay. So what we do, we simply summarize all the weights, and then we pass through an activation function. If the activation is as simple as whether this is greater than some specific threshold. If that's the case, you are going to predict that, oh, this would go off chip. So this is what the entire pipeline looks like. Now, how exactly you can train this thing? Right? So this is like, is this like a normal machine learning training that it would probably also take too much of compute resource? The answer is no. So let me give you one example, like how exactly the training happens. So let's take this example for now. So let's say you have a load request. You went through all of this and you predicted that, okay, it would go off chip. But in reality, let's say that did not go off chip. So what does this mean? This means let's backtrack, right? So it's a manual, let's say, back propagation. Right? So let's backtrack. So what does it mean? It means that this activation should not happen, right? So that means that the sum of weight should not be higher than the activation threshold. So that means whatever you got, this individual value, it should be lower than what you are getting now. So what you do, you again look up this same thing with the same features that you actually made this prediction with. You look up this individual weight table and you just simply decrement each individual weights. So it's basically just a direction, right? So it's a Boolean direction. So if your prediction is on the correct direction, it means that, okay, whichever direction you're going, you just reinforce on that direction. If it is wrong, then whichever direction you went to, you need to come back. So that's what, just a decrement operation. So by just simply using increment, decrement, and this is integer increment, decrement, it's not also floating point. So you can actually make use of these sort of predictors, and we have code for this. Is this clear? Or any other questions in this direction? Okay. So if not, so then let's see some evaluation. So these are the extensive evaluation study we did with ChamSim, many single core, 8-core configurations. We also evaluated against multiple types of prefetching mechanisms, and there are some proposals in the literature that can be either they are proposed for off-chip prediction but in a different way, or they can be like for this example, this HMP it was proposed for a different reason, but you can also repurpose it for off-chip prediction. And then we also have an idealistic version of off-chip predictor, meaning like, oh, if you magically know that this would go off-chip, what would have provided? So whenever you are doing research on the ideas in computer architecture, it's always good to ask yourself the question, what is the headroom? So if you are working with some sort of speculation, it's a good idea to ask yourself, if I know the correct outcome, what the performance that you can get. So that's what this ideal off-chip prediction is going to give you. Like if you magically know that this is the fate, what you could have done. So I'm not going to go through these details, but this is what the performance looks like. So on the x-axis, you have different workload categories. Y-axis, you have different, the performance. Again, higher is better. What I'm showing over here is Hermes, which is the proposal that we did now, and compared against Pythia, which we just showed before. That's the prefetching mechanism. So what we can see over here is that by itself, Hermes is not as performant as Pythia. Why? Because that's obvious, because Pythia not only like it can anticipate much ahead of time that, oh, your program is going to need this in future. But Hermes can't. Hermes waits for the program to generate the request, and then it speculates, oh, yeah, I mean, it would go off chip. So let's start fetching the data. So inherently, it has lower timeliness than a prefetching. So it can anticipate not as far as a prefetching. So that's what, that's why we are seeing that Pythia by itself is providing much more high performance. But the good part is that this almost half of the performance benefit is coming at 1/5 of the storage over it. So bang for buck is higher over here. And the other thing is that if you add both of these mechanisms on top of each other, so you not only have off-chip prediction, but also have prefetching, that additionally provides performance benefit. This, again, I'm just going to foreshadow a bit. So this is the average case behavior. That does not mean that every workload-wise workload, this is getting additive benefits. So in many workloads, you would see, and that's what the third work is. I'm going to give a brief overview. Many workloads, you would see that these two mechanisms actually destructively interfere. Like one kills the other one's benefit. If you let it run individually, they are good, really good. But if you let it run in combination of each other, they actually destructively interfere. So in general, you see performance benefit. That does not mean that workload-wise workload, that's not the case. Okay. So yeah, so that's what we showed, and I'm going to probably skip through these slides also. But the core part of the or the key takeaway here is that it not only gives you performance benefit, but also it's super accurate than a prefetching mechanism like Pythia. So it also increases, or it also incurs less DRAM overhead than what a prefetcher would have done. So yeah, so there are other evaluation strategies, and maybe I'll stop and explain this figure a bit, and then go to the next one. So on the x-axis, you have different bandwidth. You have seen this sort of chart in the Pythia. I showed this, and then this is on the y-axis. You have the geometric performance. 1 meaning that anything lower than 1 meaning it's bad. 1 meaning that if you don't do any of these things, this is what the performance should be. So you should not go lower than that, for sure. So this is what Pythia and Hermes does. So at some point, you can see this is the inflection point, right? At some point, the more you bandwidth constraint you go, Hermes actually starts providing more benefit than Pythia. Why? Because Pythia has some sort of inherent bandwidth awareness, but it still provides tanking performance in these cases. So if you have only Hermes, that actually provides better benefit. But then if you add both of these mechanisms together, so if you see that black line and the blue line, it increases the blue line for sure. But if you see that is the black line is maximum of the orange and blue, that's not the case. You can easily see here that the black line is literally closely following what the blue line is supposed to do. So what essentially I'm trying to say is that in this realm, where Hermes is actually better than Pythia, your combination is still closely following Pythia. It's not actually following Hermes. So what happened? So it should have been maximum of both, right? I mean, come on, computer architects, we are supposed to solve this thing. So that's what, I'm just foreshadowed some of this. And that's actually the part of the last work that I'm going to present over here. And again, like all of these things are, so I'm just going to summarize before going to the next work. So we are basically advocating for off-chip load prediction, which is kind of a different form of speculation than what prefetching does. And we showed that, okay, it can either be applied by itself or it can be combined with load address prediction, which is made by prefetchers to provide performance benefit. And many of these, all of these codes, like, all the prefetchers, all the workload traces, or all these sort of prefetchers, you can see like when they're published, and all of these off-chip load prediction mechanisms, they are all open source. So if you want to work on this thing, it's a good thing to work on. So I would just once go back here. So even with all of this intelligence, we are operating at 77% accuracy and coverage. So you can easily imagine like it can go higher. And if you go higher, it would actually give more performance benefits. So that's one thing that you can easily work on, that if you are interested. And the code that we have over here, it's also pretty easy to extend. Like all you need to do is that there is a base class. All you need to do is just to extend this to functions, C++, easy. And then you would get numbers like this. So this is the true positive, false positive, negative, false negative, and this is the precision recall. So yeah, if you want to make your hands dirty, that's a good option. And if you have, there is a good need for improving the accuracy and the precision of these things, because these things are also getting implemented in real processes. So it's maybe, it's a good direction to chase for also. Okay. Okay. So as I said, so this is what the paper is. If you are interested, then take a look at it. So when I start, stop, I would probably take 5 minutes, I think. Is it fine?
It's fine. We don't
have a break, I guess. Okay. So maybe I'll take 5 more minutes for the, before switching for the break, and then we can go to Rakesh. So what I just kind of foreshadowed, that I showed you Pythia, I showed you Hermes. Both of these are targeted towards the same thing. Memory latency is the problem. Let's try to do something. They take different approaches. It's a data prefetcher that predicts address. It's an off-chip predictor that it does not predict address, but it predicts which request would go off-chip. So it's like you are aiming big, but if you miss, you are also missing big. In this case, you are aiming small, so you are not predicting the full address, you are just predicting a Boolean value. But if you are also missing it, you would probably also miss small. So the negative side of this is much lesser than what this can do. So what I showed before, that these two are supposed to be implemented together, but we don't know how exactly they behave together. So that actually brings us to this final piece of work, which we just presented, I think, a couple of months. Yeah, it's already a couple of months back in Sydney. So this is called Athena, synergizing data prefetching, which we already saw. Pythia is one example, and off-chip prediction, which Hermes is one example, via online reinforcement learning. Again, RL comes back to the rescue. So what we showed here, and I'm going to keep it a bit high level for this work. So what we showed over here is that off-chip prediction and data prefetching, they are often good together, but they also provide complementary performance benefit. Complementary meaning that this is what I'm writing over here. Especially in memory bandwidth constraint scenarios, off-chip predictor actually works really well as compared to prefetching. But the worst part is that if you just simply fuse them together and just implement them together, that does not work. So enabling both mechanisms often negates performance benefit of each individual mechanisms. So that and there has been proposals in the past that not exactly tackles this specific problem of managing off-chip predictor and prefetcher, but there has been works on managing multiple prefetchers. So if we do those mechanisms for these work, like this coordination, that also falls short. And I'm not going to go too much into detail like how exactly it falls short, but if you're interested, definitely check out the paper. So what the goal of this work is that, okay, let's design a holistic framework that can synergize these two complementary mechanisms, which are supposed to be complementary, right? So these two complementary mechanisms to deliver consistent performance benefit, irrespective of what workload that you're looking at, what type of system configuration that you're looking at. So that's what Athena is. So it basically, we're trying to formulate this coordination via reinforcement learning. So what we are doing here, Athena acts as the RL agent, whose goal is to autonomously learn this coordination, and your processor acts as the environment where exactly Athena is going to reside. So what it does, it basically, unlike Pythia, what we showed that, it extracts features like which memory instruction generated this request, what is the sequence of addresses that you have seen in the past, Unlike that type of state, what Athena does, it actually takes system features from literal system, like, oh, what is my bandwidth usage? What is the prefetcher's accuracy? What is the object predictor's accuracy? What is the cache pollution? It takes all of this information together and takes a coordination decision. So in this case, coordination decision is not only to enable each of these mechanisms, like which one to enable or which one to disable, but also if you're enabling prefetcher, it can also dictate what aggressiveness it should be enabled with. Like, should I be very aggressive? Should I be somewhere middle of the road? Should I be very less aggressive, or should I completely throttle it down? And so it can also do that. So that's the action. And what is the reward in this case? The reward is essentially telemetry information. So unlike Pythia, when we saw the reward, like all of those hard-coded parameters, like you ask the question, like, why those hard codes, right? So here in this case, that actually gives you, let's say, a path of not hard coding. So this is raw performance, and it's learning from the raw performance. So what we are, the telemetry information is like, oh, I made this action, I made this decision. Does this improve the IPC? Does this improve the number of LLC messages? So these sort of actions you are taking and feeding it to Athena as a reward. But then you can easily, let's say, argue to yourself that, wait a sec, if you see a change in IPC, like, oh, your performance is increasing, how exactly would I know that it's my workload is probably changing, or is it, let's say, something good that I did, right? So that can be a legit question. So it might be very much possible that, oh, you were, at some phase, you are actually reading from file. If you're reading from file, that's IO. So definitely your IPC would be lower in those cases as compared to, let's say, once you read the file, then you started operating on the numbers that you read, right? You're just simply adding or subtracting or, doing matrix multiply or whatnot. So what I'm trying to give you a hint is that just doing this raw performance understanding and feeding back to the RL agent can also be dangerous, because it's not actually telling you that whether your workload itself is changing or something else is changing, right? So for that, we also have some sort of, let's say, guard bands. Let's say, oh, let's try to see how many load instructions we have executed, how many mispredicted branch we have executed, just to basically understand that, okay, have our workload fundamentally changed or not? So this sort of information is also there. Okay, so we have also done like an extensive study. I'm not going to go into detail. Again, everything is open source. And this also actually got the artifact award. So if you're interested, definitely check out the paper, check out the artifacts, which I have put over here, all the links. So these are some key results that we are going to show. So before going back, so what we are essentially here showing over here is that different types of design points. So you're seeing here the off-chip predictor with one prefetcher that is sitting at L2 cache, maybe one prefetcher at L1 cache, two prefetchers at L2 cache, one prefetcher at both at L1 and L2 cache. Like basically what we are trying to demonstrate is that if you have this sort of RL mechanism, you just do it once and it would seamlessly adapt to different type of configuration that you're throwing at it. So, and that's what we are showing over here. So for every case, you have workloads on the x-axis, speed up on the y-axis, so higher is better. And you have the naive combination, which is basically just to fuse together, and best prior combination policy that we had before, and then what Athena is providing. So in all the cases, what you can see is that it does not depend what configuration that you are operating with. Athena with the same configuration parameters, like we are not changing any hyperparameters for this 4 evaluations. With the same hyperparameters configuration, it still end up winning in all the configurations. So that gives us some understanding that yes, it can provide performance benefit. So that's what we are writing over here. So it provides consistent performance benefit. We have, like in the paper, we have done lots of other evaluations, like varying the prefetchers, varying the off-chip predictors, and we showed that it still works decently good. And then the storage over it is also pretty lightweight. So that's a good point on top of this. Okay, so that kind of closes down the first part of the lecture. I think we can take a break, 5 minutes maybe. Okay, so we would meet in for 20. Okay, so let's meet in 5:20, and then Rakesh is going to give you on the storage side of the story. Thank you very much.
By the way, there are a lot of people.
Is it yours? That's not. Start.
Yes, please. Now it's done.
Oh, okay. Test. Okay, so let's switch to the second part of this session, and we'll look at how we can use reinforcement learning in storage systems. And here we look at a particular type of or category of storage systems, which are called hybrid storage system, where you have multiple storage drives in a system that are basically serving your data, storing data, and giving you access to the data with different characteristics. So these kind of storage systems you would find in all places, enterprise data center environments, where you have fast devices where you store the most important data that you need, and then slow devices where you have large capacities and you basically store data for long-term storage. So I'll present this work called Sybil, which is basically looking at adaptive and extensible data placement in hybrid storage systems. And we use reinforcement learning to do that. And this paper was presented at ISCA 2022. So before we look at what we are doing here, we just try to see what is there in the real world, what kind of data placement techniques are there. So I'll just give a brief introduction of what a hybrid storage system looks like. You have a fast device, which is an Intel Optane SSD, which is very high, and you would have access latencies in the order of 10 microseconds or even less. And you have a slow device, which is a hard disk drive that you have. You see commonly in every desktop or a server class system, which has access latencies in the order of milliseconds. Now, if you connect these two devices or more devices in a system, basically who manages these storage devices? So you have a storage management layer, which basically interfaces with the application or file system, and then it provides a unified logical address space that kind of gives basically reads or writes data from that to the storage management layer, and this orchestrates the request from the application to one of these drives. So depending on where the data is stored, it would basically read the data from there. And when you want to write the data, it has to decide where it has to go to. Now, if you think about this problem, it's not a very simple problem to solve, because you have a lot of things. As Rahul mentioned, the workloads can change over time. And depending on the workload, you also need to adapt these policies to basically store the data in a particular disk. So if you need if you want to store several pages of data that you don't need for a long time, you basically don't want to store it in the fast device where your capacity is low and you basically don't access it for a long time. So you're taking away space from more latency hungry applications which may need to store data here. So basically the storage management layer is what orchestrates these requests. And you also have this migration policy that this storage management layer handles, which basically is similar to what Rahul mentioned, which is basically prefetching data from the slower device to the faster device, or evicting data that you don't need from the faster device to the slower device. So we call it promotion and eviction. So with that, the performance of this system is highly dependent on the HSS or the storage management layers,
ability to manage these diverse workloads and the devices. So these, as you saw, the devices have very different characteristics in terms of its access latency, in terms of the capacity, the bandwidth that it provides, and so on. So when we looked at the prior techniques that are out there, we observed two key shortcomings. The first one is the lack of adaptivity to workload changes and changes in device types and configuration. So you have enterprise environments where you always do hot swapping of these devices, plug in a new device or remove a new device for servicing, or basically many such cases where you have to adapt to these conditions. And then extensibility. So if you add 100 more devices, how do the policy adapt to those devices? So we looked at basically some policies that are that you can call them state of the art, and we looked at the performance of these policies. And basically, when we try to compare it with an Oracle policy, as Rahul mentioned, you need to see the headroom of this an approach that you are trying to design, or a technique that you are trying to design. And we compared the two policies that we have. One is called CDE, which is a heuristic policy, where you have fixed thresholds to determine, okay, I will place 90% of the data in my fast device. After that, everything goes to the slow device. That's one of the approaches. Then there is a supervised learning approach called RNN, which basically tries to predict the access frequencies of the pages in the future, and then determine where to place the data, or where to basically move the data. So when we looked at this, these policies, and then compared it with an Oracle approach, which has complete knowledge of the future access pattern. So you basically give a workload to the Oracle. It knows what happens in the till the end of the workload, the lifetime of the workload, and it makes decisions based on that. So that's the kind of the upper bound that we are looking at. So here we found that this is basically showing the performance in terms of average request latency. So lower the bar, the better it is. So when we looked at these workloads, we found that there is still a large gap in terms of performance of these policies compared to an Oracle, which actually shows that some of these policies are statically tuned and they are not basically adapting to the workload changes. Then we look at changes in the configuration itself. So we saw that we see several policies here. We compare it with an extreme worst case scenario, which is called slow only. So all the data that you want to store is going to slow only device, or the slowest device. And then you have the other two policies and Oracle. So in one configuration, you see that the slow only device is actually performing much better than the heuristic approach. But if you change the configuration, the same policy actually performs better. So these kind of configuration variations actually affect the performance of the policies. And this is because they don't really consider the underlying storage device characteristics. So what are these characteristics? So if there is a change in the latency that the device is operating at, the read-write latencies, or when there is garbage collection happening within these devices, you would find that the latencies increase. So these the variations that happen in the system are not considered by these approaches. And when lack of extensibility is another major limitation of these prior techniques. So these are very rigid techniques that require significant effort to accommodate more devices. So if you have two devices, you would design a policy that basically can do well for these two devices. But if you add another device, you need to change the policy itself or design a new policy. So with that, our goal was to propose a data placement mechanism that can provide both adaptivity to changes in workload and HSS conditions, also easy extensibility to different configurations. So this is Sybil, which basically formulates data placement in hybrid storage systems as a reinforcement learning problem. And I will not go into the basics of RL again. Rahul has already covered it. So, but how we design Sybil is like this. So we have the agent, which is Sybil. The environment is the hybrid storage system. Sybil looks at the features of the current request in the system from the environment, and it performs an action, which is to select a storage device to place the current data. And the most important thing, which is the reward, is the request latency of the last served request from the environment. So we look at the state in a bit more detail. So we consider a very limited number of state features. We do a lot of experimental analysis to find which features are more important. And we basically want to reduce the implementation overhead. If you have more features, you basically have to store them, and that adds to the overhead. Then we also observe that RL agent is more sensitive to reward. So we have a 6-dimensional vector of state features, which includes things like size, type, the access interval, access frequency, the capacity, and so on. And we basically quantize the state representation into bins to reduce the storage overhead. Now, if we look at the reward is the most important part, which determines the objective of the RL agent. And we formulate the reward as a function of the request latency, because that's the thing, that's the kind of metric that we are seeing from the HSS or the storage management layer. So what this request latency gets is gives us is basically, it encapsulates 3 things. One is the internal state of the device. So if you have a lot of requests queued up in the system, then it also accounts for the queuing delays. If there is garbage collection happening, then you get the latency of that. You basically experience the latency increase in when there are variations happening in the system. Then you have evictions, which are also considered when there is a latency. So what happens in eviction? So if your fast device reaches its full capacity, then when you have to write the data to the fast device, you basically have to evict some data from the fast device to the slow device. So that is also being considered in the latency of that operation is considered here. Then we also take throughput into account. So basically the reward is considering many factors that happen internally within these drives. Then the action, as I mentioned, is to basically select a storage device for placing every new page request. And the action is also easily extended to any number of devices, because you basically have a lot of, if you have a lot of storage devices, you just need to determine where it has to be stored. And Sybil also evicts a page when the fast device utilization is 100%, and it promotes a page when there is an update from the application. So I'll give a very brief overview of Sybil. So Sybil has a 2-threaded execution model. It has a decision thread, which makes the inference and basically takes the storage request from the operating system and decides where the data has to go into, which is the data placement decision. Now, there is a training thread which runs in the background, which basically takes the state, reward, and action information from the decision thread, and then it trains an RL agent or the neural network in the training thread, and then updates the weights of the neural network to the decision thread. So I'll go into more details of this, but there is a background thread which basically does all the learning, and then updates the foreground thread, which is making all the decisions. So this kind of asynchronous execution is done to reduce the overhead on the IO request. Now, if you look at it more closely, this is the 2-threaded execution where you have the decision thread. So if you look at when there is a storage request from the application or from the operating system, we basically extract the observation vector that I just showed before, where you take the access frequency, the access interval, and so on, and then use that as a state, and then provide that to the inference network, which basically gives you an action, which is to perform the placement in the HSS. Now, the inference network's objective is to basically maximize the reward that the HSS provides. So when the HSS provides a reward to the RL agent, we basically take the observation, the state from the observation vector, the reward and the action, and then use that as an experience. So here we store those details in an experience buffer in the host DRAM, and we basically then go to the training thread. So you have the experience buffer of a large number of requests in here, and then you take few samples of the experience buffer, use that as the training data for the training network, and then you train that network and then basically perform policy updates frequently with the inference network. So this is a kind of an asynchronous execution that helps us reduce the overhead on the storage request in terms of making doing both training and inference in the same thread. Now, any questions so far? Okay, so we'll jump to the evaluation of Sybil. So what we do is we evaluate this policy in a real system. This you can see is a desktop class system where we have multiple drives connected to the system. We look at two configurations, a dual hybrid and tri-hybrid system with different drives. We have a cost-oriented configuration, which is having a high-end Optane device and a hard disk drive, and a performance-oriented configuration with a high-end SSD and a middle-end SSD, which is basically the latency gap between these two is considerably less compared to this one. So we evaluate 18 different workloads from different benchmark suites, and we look at 4 baselines, 2 heuristic-based and learning-based, 2 learning-based baselines. So if you look at the cost-oriented configuration, so what is the performance here? So again, we show the normalized average request latency on the y-axis. So what are we normalizing it to? We look at a very ideal configuration, which is the fast-only configuration where we store all data in the fast device. And that is the normalizing factor here. So basically, you can see here that Sybil in the red bar is outperforming all the other baselines in most cases. And if you look at the performance-oriented configuration, we see that, again, it outperforms all the other baselines, but also provides 21.6% improvement in performance by dynamically adapting its policy. And it achieves 80% of the performance of an Oracle. So that's about the performance. Now we looked at how we can extend this to more devices. And extending Sybil to more devices is kind of easy. We have to add a new action to the RL agent, and we have to provide the remaining capacity of the new device as a state feature. So when we did extend to 3 devices, we observed that compared to a heuristic approach, which basically has a lot of thresholds to determine where the data goes to if there are 3 devices, our approach basically performs much better. We see a 48% improvement in performance in a tri-hybrid system. And adding these two, extending Sybil to more devices is not so difficult. So it basically provides the ease of extensibility. Now the overhead is also very minimal. So we consume, or the Sybil agent consumes around 125 kilobytes of total storage cost for experience buffer and other aspects of Sybil. Then we need 40-bit metadata overhead per page. So we need to store the features of the incoming request and the HSS. So we need to we store some metadata in the host to do this, and our inference latency and training latency are significantly less. So we don't add a lot of overhead on the IO request. So there are more details in the paper I'll not go into. We provide a lot of analysis, and most importantly, we also give some explainability analysis, because RL is traditionally looked at as a black box. So we basically have to explain the actions of the RL agent and give insights. So that's also an important part which we show in the paper, right? So this is the link to the paper. I encourage everyone to take a look. So in conclusion, Sybil is the first RL-based data placement technique in hybrid storage systems that provides adaptivity, extensibility, and ease of design and implementation. We evaluate Sybil on real systems with different workloads. We get good performance improvement compared to the best to the prior techniques. And when we extend the policy to multiple devices, we see even better performance improvement. And we also achieve 80% of the Oracle's performance with low storage overhead. So that's about Sybil. Any questions on this? We still have some time. Okay, so what we'll do now is we looked at data placement as the key problem that we are solving with RL agent here. In our next work, which we'll present in a couple of months at ICS, we looked at how we can look at migration as well, which is an even bigger problem in terms of scale. So you basically have multiple devices in your system and a lot of data stored in each of these devices. How do you find out which device, which page is becoming cold, and you have to move it to the slower device? Which page is becoming hot and you have to move it to the faster device? So that's a challenge that is difficult in terms of scale, because you have a lot of data and you need to see how you can do that. So in this work, Harmonia, we are looking at a coordinated data placement and migration policy using multi-agent reinforcement learning. So I'll not go into a lot of details of this background. Again, you have here we show 3 devices, and we have a data placement policy and a migration policy. So this again is very similar to the prefetching and eviction policies that are there in the cache hierarchy or in main memory. So so here we looked at again what can be improved here. What can we improve compared to the state-of-the-art techniques? And basically, we found that there are 3 key shortcomings. One is all these policies, including Sybil that we saw before, don't optimize both data placement and migration. So in Sybil, what we do is we looked at in terms of migration, what we do is when the fast device capacity reaches 100%, we move the data to the slower device at that point, because the main objective is to reduce the performance of or improve the performance of data placement or reduce the latency of the IO request. Now, all these prior techniques don't optimize both placement and migration. Then we decided to kind of explore this area, and then we tried to combine state-of-the-art placement and migration policies, and we observed that naive combination of these techniques don't actually give us the performance that we need, and that's because of lack of coordination. And then extensibility, as I mentioned, is a problem when we also look at a large number of devices in the system. So here, in terms of holistic data management, we basically looked at the performance of some of the same baselines that we showed before, but also looked at Sybil as another baseline and compared it to an Oracle, which has knowledge of all the access patterns. And we see that there is still a large gap because if you have a lot of migration, then we see that there is a large gap in terms of performance of an Oracle and Sybil. So this is because that Sybil ignores the data migration part and tries to optimize the placement part. And then we looked at now we can try to combine the state-of-the-art placement policy and the migration policy, and let's see the performance. So here we see that when we combine these policies like Sybil and KSVM and Sybil and RNN HSS, which are the state-of-the-art placement and migration policies, we see that the performance even becomes worse than Sybil because of lack of coordination. Because when you integrate these 2 policies, you have to integrate it in such a tight manner that they know that one policy knows the other policy's decisions, which is not the case when we do a naive combination of these approaches. And then lack of extensibility is the same as I mentioned. So you need to design a new policy when there is a change in the device or when you add more devices. So our goal was to look at a holistic data management mechanism that basically optimizes both data placement and migration, achieves coordination and also extensibility to a large wide range of HSS configurations. So this work proposes Harmonia, which looks at combined optimization of these policies also tries to establish coordination between the two policies and also achieves extensibility. So in this case, again, if you look at this RL formulation figure, so we see that there are two agents, a data placement agent and a migration agent, and both look at the state features from the environment, and both provide and perform an action which changes the environment in every step. And then you get a reward from the environment for both the agents. In this case, what we see is like in Sybil, the placement agent gets an immediate reward. So after every placement that you do, you get an immediate reward from the environment. This reward is basically telling the agent, okay, you're now doing well, or you're doing badly for this workload. That's one way to tell the agent to adapt to the changes. In case of migration, it's a difficult problem because the effect of migration is not seen immediately like the placement. You don't get the latency of migration immediately because the effect of migration is only seen by the future placements that you perform. So we provide a delayed reward for the migration agent. So in terms of state, we again have a limited number of state features. We also include some more features here, like the migration interval. This is because we want to avoid ping pong migrations. Basically, if there are two devices, your placement agent places in the fast device, but your migration agent comes and takes that page and then places it in the slow device. We want to avoid those kind of situations, so we add a migration interval feature, and we again quantize the state features. In terms of reward, what we do is we provide a reward which is again a function of latency to the placement agent. But in terms of migration, what we do is we look at the placement after we perform the migration of, let's say, 10 pages. We look at the latencies of the future requests that are coming in. So we look at the latencies of 50 pages that come after the migration is performed, and then determine basically create the reward for the migration agent at that point. We also have a migration penalty that we provide to avoid this ping pong migration. So in terms of action, both have a very simple action space, which is to select where the placement agent basically selects where the data has to go into which storage device. Migration agent also, in addition to selecting where the data has to be migrated, it also picks which pages have to be migrated. That's another feature that we add in this migration agent. Again, because of the action space being very small, we also can extend it to a number of storage devices. So in terms of Harmonia, what the design itself, what we do is every new request that comes from the application, whether a read or a write, it goes through the data placement agent, write mostly. It has again a two-threaded implementation, and it decides where the placement has to happen. Now, as you run some workloads or place a lot of data, your hybrid storage system is having a lot of data in many devices. So then what we do is we look at, we have a data migration agent that looks at the data that was previously stored in the hybrid storage system. Again, this also has a two-threaded implementation, even though this completely runs in the background. It doesn't have to, it doesn't have the constraints of the critical path of the IO request. So it completely runs in the background, and then it decides what are the candidate pages that needs to be migrated and puts them in a migration queue. And there is a migration thread that is running in the background, which basically tries to look at idle times and also the bandwidth of these devices to figure out, oh, when can I migrate those pages? We don't want to, because both the placement and the migration are sometimes happening on the same device. We don't want to step on each other's shoes. So basically, we look at idle times to perform these migrations. And then by using the reward, we actually do the coordination between the two agents. The design is quite similar. We have a two-threaded implementation. I will not go into this. In terms of, again, the evaluation methodology, we have a real system. We evaluate all our policies on this. We again look at two configurations that we saw earlier. But we increase the evaluation space. We look at data placement policies, migration policies, and also extended techniques that we mentioned. Something of interest here is that we looked at whether do we need two agents for this problem at all. Can we do everything with one agent? So that SAPM is a single agent placement and migration policy. Then we look at newer workloads. We choose 17 workloads from YCSB benchmarks, all enterprise benchmarks, and also some machine learning workloads which are using ResNet and cosmology, parameter prediction workloads. So in terms of performance analysis, we see 32% improvement over Sybil, purely because we have a coordinated policy for both placement and migration. And we achieve 64% of an Oracle's performance. In terms of cost optimized HSS, we again see a significant improvement in performance. We see our 33% improvement. Again, we bridge the gap between Sybil and Oracle. In terms of extensibility, we look at 3 and 4 devices configurations. In the paper, we also look at a persistent memory device, which is quite interesting because that has a very significantly higher latency than the high-end device. So in this case, what we see is that the performance improves as we saw in the previous work, because all these heuristic policies or even Sybil has to kind of, the migration policy in Sybil particularly has to accommodate these newer devices or the large number of devices. So there is some heuristic involved there. So again, the overhead is kind of acceptable. The part that I did not mention is because we have more agents now, we are reducing the overhead or the size of the agents. Basically, we don't have as many hidden layers. The nodes in each agent are also fewer than what we have in Sybil. So that is an interesting part that is there in the paper also. A lot more experiments that we look at. We also see convergence. So we basically have to figure out, okay, now there are 2 agents running. Are they even coordinating? When are they coordinating? These are some aspects that we experiment in this work. So we look at the convergence. We look at uncoordinated RL agents. So what happens if you don't achieve coordination? So these are some interesting experiments that we have in the paper. This is the link. We will have a improved version quite soon. So in conclusion, this is the first work to use multi-agent RL to optimize data management in HSS. We see significant performance improvement, and this performance improvement increases when there are more devices, and the overheads are quite low in terms of inference and storage. That's the second work that we wanted to look at in storage systems. Any questions so far? Okay. So to summarize, the challenge and opportunity for future is to basically have more self-optimizing computing architectures. The data is increasing that we generate or we consume is increasing every day. So we need to have a more self-optimizing architecture which adapts to these changes or adapts to the data and then makes more wise and good decisions. And our goal is to become something like this, which is a self-optimizing architecture that is there in everyone's head. And our goal is to become something like this, where it constantly or continuously adapts to changes in the environment or changes around us. And we try to learn from the surroundings. So this is basically the last slide, and we conclude here. If there are any questions, we can discuss or we'll call it today. Okay, thank you so much.
So maybe also a reminder for your presentations to get in touch with your mentors in time.